So, have you ever stubbed your toe and just immediately jumped back, like way before you even fully registered the pain? It feels completely instantaneous. But how exactly does your body solve this massive biological problem of instantaneous movement? Well, the answer actually lies in an incredibly precise microscopic relay race that's happening inside you right this very second.
Welcome to the Explainer. Today we're zooming in on Module I of the Neuropsychology syllabus, specifically looking at the foundational biological mechanisms of the action potential and chemical synaptic transmission. We're going to break down exactly how a nerve impulse is generated, how it physically travels, and how neurons manage to communicate across tiny little gaps to keep you moving, thinking, and feeling.
Okay, let's dive right into this. Here is our roadmap for today. We'll start with the resting potential, trigger the explosive action potential, see exactly how the body speeds that signal up, cross the gap via chemical transmission, and finally look at resetting the system. Starting with number one, the resting potential, the neuron at rest. Now, before a neuron even fires, there is this incredible amount of tension building up inside it. I mean, it's not actually resting in the sense of just lounging around doing nothing. It's actively, aggressively preparing. As you likely already know, the body invests a massive amount of energy into the sodium-potassium pump. This pump is constantly working to push 3 sodium ions out of the cell for every 2 potassium ions it drags back in. It's really helpful to think of the resting potential of a neuron exactly like a poised bow and arrow. An archer who pulls the bow back in advance is ready to fire the very second the moment is right. The neuron uses that exact same strategy to guarantee a lightning-fast response. And because of this setup, you end up with 2 invisible physical forces that are just constantly acting on the sodium ions outside the cell. First up, the electrical gradient. The inside of the cell has a negative charge, which violently pulls at the positively charged sodium ions. Second, the concentration gradient. Sodium is more than 10 times more concentrated outside than inside, so it naturally just wants to flow inward to balance things out. Basically, sodium is totally desperate to get in, but it's stopped by the cell membrane's tightly closed gates. But, that tension can only hold for so long. Eventually, a stimulus occurs, the threshold of excitation is reached, and that brings us to section 2, the action potential, releasing the arrow. Now, what's really interesting here is how this perfectly illustrates the all or none law. Any stimulation beyond the threshold produces a massive response, totally regardless of how far beyond the threshold it is. The textbook actually gives this brilliant everyday analogy. Imagine flushing a toilet. You have to press the handle with a certain strength, right? That's your threshold. But pressing the handle harder or, faster, it doesn't make the toilet flush any more vigorously. The action potential works the exact same way. Its amplitude and velocity are entirely independent of the intensity of the stimulus that started the whole thing. When that threshold is hit, it triggers this explosive sequence. The voltage-gated sodium channels open wide. Driven by both the electrical and concentration gradients we just talked about, sodium ions rush rapidly into the cell, entirely reversing its polarity. Then, at the absolute peak of the action potential, those sodium gates snap shut. Almost immediately after, potassium channels open up, and potassium ions rush out of the cell, carrying your positive charge with them to restore that original negative balance. This dramatic snapshot mechanism of the sodium gates kicks off what's known as the refractory period. Because those gates are tightly closed and absolutely will not reopen for a brief moment, the electrical charge literally cannot flow backward. It's honestly a brilliant biological design. It ensures the signal only travels in one direction, forward, down the axon, and prevents the cell from just misfiring endlessly. But here, we run into a bit of a biological problem: distance. Which brings us to number 3, speeding up the signal, the myelin sheath. In unmyelinated axons, this impulse travels at less than 1 meter per second. So how does this electrical impulse travel fast enough to serve a giant animal, like, say, a giraffe, where a signal has to go all the way from its spinal cord down to its foot? To solve this, vertebrates evolved a massive upgrade, the myelin sheath. As a quick refresher, this is that insulating material composed of fats and proteins that tightly wraps around the axon, basically preventing the electrical charge from leaking out. And this brilliantly illustrates how myelin actually speeds things up. You see, the myelin sheath isn't continuous. It's interrupted by these tiny little gaps called the nodes of Ranvier. So instead of the action potential slowly regenerating at every single microscopic point along the membrane, the electrical charge literally jumps from node to node.
This is called saltatory conduction, from the Latin word saltare, which means to jump. It not only massively boosts the speed of the signal, but it also conserves a ton of cellular energy in the process. Moving on to number 4, chemical synaptic transmission, crossing the gap. All right, so our electrical sprint has reached the very end of the axon, but neurons don't physically touch each other. There is a microscopic gap. This means the electrical signal must now be converted into a chemical one to actually cross that gap. This chemical baton pass happens in a highly specific 4-step sequence. First, the neuron synthesizes neurotransmitters and stores them in tiny spherical packets called vesicles. Second, when the action potential reaches the terminal, it opens calcium gates. This sudden influx of calcium triggers exocytosis, basically a burst of neurotransmitters released right from the neuron. Third, these chemicals diffuse across the gap. And fourth, they bind to receptors on the receiving cell. Now, this gap, the synaptic cleft, is incredibly narrow. We're talking only 20 to 30 nanometers wide. Just for some historical context here, early scientists like Charles Sherrington didn't even believe a chemical process could be fast enough to account for our reflexes. He simply couldn't imagine a gap this unimaginably small, allowing chemicals to diffuse across it in less than 1/100th of a millisecond. I mean, it's wild.
So the crucial point is what happens when those chemicals actually reach the other side. They basically have two main ways of interacting. First are ionotropic effects. Imagine a paper bag twisted shut at the top. When the neurotransmitter binds, it instantly untwists and opens the channel. This is the brain's rapid on-off switch, used for super quick visual or auditory information, and it heavily relies on the transmitter glutamate. On the flip side, we have metabotropic effects. These are slower, but they initiate complex cell-wide metabolic reactions using second messengers inside the cell, which influences activity over a much longer period of time.
Which leads us to number 5, resetting the system, clearing the cleft. Look, once the message is received, that synaptic cleft has to be cleared out immediately. If the neurotransmitters just lingered around in there, they'd keep exciting or inhibiting the receiving cell, and the neuron would be entirely useless for any future communication. Let's see how the body builds a perfectly sustainable system here. It recycles and it does it efficiently. Some transmitters, like acetylcholine, are broken down by enzymes right there in the cleft. Others, like serotonin and dopamine, detach and are reabsorbed whole by the presynaptic cell through special transporter proteins, a really cool process called reuptake. Plus, the receiving cell can even send negative feedback chemicals, like cannabinoids, back to the sender, essentially saying, hey, message received, you can stop sending now. So we've just traced the entire lifespan of a single signal, a resting potential building up tension, an explosive action potential rushing down a myelinated axon, and finally, a delicate chemical dance across the synapse. It really is a masterpiece of biology. But I want to leave you with this thought. If a single neuron operates as this highly complex, perfectly timed biological battery and chemical factory, what kind of universe is created when 86 billion of them fired together in the human brain? That microscopic relay race is literally the foundation for every thought, feeling, and memory you will ever have. Thank you so much for joining me on this explainer, and keep questioning the incredible mechanics of your own mind.